Well, good morning, everyone. Hope everyone had a good weekend. Things are working out okay. I guess we're going to be talking about a little bit of review today. So we're looking at a review of the last couple of chapters, which are going to form the third unit for the course today. And I guess I'll go over some of the homework problems that were done, maybe a couple little things that I want to clarify on homework and stuff like that. By the way, say hello if you're in chat right now. I'd really appreciate knowing that there are folks keeping an eye on things here. I show a couple of concurrent viewers here, so I guess there's a few folks that are watching today. But yeah, let's jump right in. Again, if you have questions, don't wait for me to pause or anything like that. Just throw them up in the chat, and I'll get to them as soon as I can. Hey, good morning, Avery and Michael. Good to see you guys. So one of the things I want to talk about a little bit is one of the homework questions that I noticed from not this past week, but the week previous to that. Hey, Josiah. That homework question that I want to talk about has to do with the idea of gravitational potential energy, and it's this question where they said, all right, there's ground right here, and then you're holding this ball above the ground a distance of, I don't know, this is not going to be to scale, but it's like it's 10 feet above the ground or something like that. I should do that. I should use the symbols, like, since we're using feet, we might as well use, there's 10 feet. Okay, so there we go. And then there's a well. They said, again, this is not going to be to scale. But then they have this well that's 50 feet deep. Okay, so like I said, this isn't exactly to scale, but just imagine. Okay, so that's 50 feet. And then there's a ball. You place the ball, and it's, I don't know, maybe I should just make this to scale up here. So let me fix this to scale a little bit. If that's 50 feet, this is going to have a hard time being 10 feet, I guess. But let's just make this to scale so we can kind of see, so it's not quite so, so skewed. But if that's supposed to be 50 feet, then 10 feet is probably something like here-ish. So let's say I put the ball here. That's 10 feet above the ground. There's 10 feet. All right. All right. So then their question was, which of the two objects has the larger gravitational potential energy? And remember that your gravitational potential energy formula is m times g times y. Anything with a higher y, with a larger y, will have a larger gravitational potential energy. So what you have to do when you're comparing these, and there's a little bit of a subtlety to this, but what you have to, the first thing you do when you're dealing with gravitational potential energy or potential energy in general is set where your zero potential energy is. So I'm going to say that just for the sake of argument, I'm going to say y equals 0 is the ground. Okay, so then which of these two balls then has the larger gravitational potential energy? Which one has the higher amount of gravitational potential energy? It's this one. It's actually this one, because this one's gravitational potential energy, because this is this is 10 feet above 0. Okay, and just to let you know, this was, I think they said that this is 20 feet above the bottom of the well. Okay, from the bottom of the well to there. So that means this is 30 feet from here to here, because the well is 50 feet deep. This one has a larger gravitational potential energy because it has positive gravitational potential energy. This one is 30 feet below y equals 0, so it actually has negative gravitational potential energy, and positive numbers are always greater than negative numbers. So in fact, the answer to that question is this ball. Now I know a lot of folks said, well, this ball is 20 feet above its whatever its particular floor is, and this one is only, oh, sorry, I just clicked on that there. But this one is only 10 feet above what its floor is, but it doesn't matter what's above or below. You get to set what y equals 0 is, but then you can't change that in mid-problem. You can't say, well, 0 is here for this ball, and y equals 0 is here for this ball, so it's different. You can't switch it in the middle like that. You just say, if you're going to compare gravitational potential energy, so you got to pick what y equals 0 is and then use that for both of them. You could have alternatively said, and this is, you could do this stuff too. You could say, well, I don't want this to be 0. I want the bottom of the well to be 0. Okay, let's say that that's true. Well, if the bottom of the well is 0, this is y equals 0 down here, then this one has a gravitational potential energy which is equal to the weight of the ball times 20 feet, but the ball here is 60 feet above y equals 0, so it's still higher. So as long as you use the same value for y equals 0 when you're doing your comparisons, you won't be steered wrong by it. So I didn't actually take any points off of that, but I did leave feedback for folks in that particular homework problem, just mentioning that you got to use a y equals 0. Whichever ball is actually higher, further above 0 compared to this one is actually below y equals 0. If you use the top of the well as 0, the ground is 0, then you're looking at that. Either way, no matter what you use for y equals 0, the ball that's 10 feet above the ground has a greater gravitational potential energy than one that is 30 feet below ground. So hopefully that clarifies that one. Most of the other ones I think went relatively well. That was the only one where I had a lot of people have the same sort of little trip before. That all the other ones were, most people had them right without too much difficulty, I think. The only other one that I would say some folks had a little bit of issue with was let's calculate how much work was done on an object, and then what about its change in kinetic energy? And let's see if I can remember what that one looks like. I don't remember the details of that one, what the numbers were for that. But just remember that the basic idea is that the total work done by all forces, if you add up all the work done by all the individual forces to get the total work done, that will be equal to the change in the kinetic energy, which I call capital K. That'll be equal to the change in kinetic energy. So if you've calculated the work done by the net force, that means you've calculated the work, counted for all the work done by all of the forces. So when you do that, then you have the total work done. That's going to be equal to the change in the kinetic energy. So that one, for instance, it was, I think you pushed the net force on the object was 60 newtons, and you pushed it for 15 meters or something like that, and then it gave a mass of the object. So let's just write that one out just to make sure it's clear. So it's like you have this box or something like that, which is sitting on here, and you push it with a force of, the net force on it is 60 newtons, so I'll just put N there for net force. It's a 60 Newton force, and you push this box along here until you later on get the box to have moved. You've moved the box over here now a distance of 15 meters by pushing on with a net force of 60 newtons. So this is the total force. It's like you pushed on it, maybe there was friction back on it or something like that, but the net force on it is 60, so maybe you pushed it with 70 and friction pushed back with 10, so the net force is 60 that way. Then the work done by all the forces, I'm going to leave off the total here. I won't leave off the total. The work done total is 60 newtons times 15 meters. Oh yeah, and they said up here, I think they said the mass of this thing was, I'm going to guess, I don't remember what it was. I think it was 3 or 30 or something like that kilograms. I don't remember the exact number they gave. And that tripped some folks up. They thought they had to use the 3 kilograms or the mass or whatever it is, but you don't. You just get 60 times 15, you get 900 joules here. And then that's actually the exact same answer. The work done from the work energy theorem is the total work done, which you calculate as 900 joules, is equal to the change in kinetic energy. So its kinetic energy goes up by 900 joules. A lot of folks, I think, used the work energy theorem, said this is equal to 1/2 mv squared, solved for v, and then plugged it back in. That's just kind of going through extra stuff you probably didn't need to do. Because you actually use the fact that the work done is equal to the 900 joules of kinetic energy that it gained to figure out what the speed is, and then you just plug the speed back into the kinetic energy formula to find, what do you know, it's 900 joules is how much work was done. So that's the sort of, that was, I guess, the two that I thought folks had maybe the most trouble with. Are there any questions? I don't see any questions yet in the chat, and I did check the discussion boards today to see if folks had questions for the live stream from folks that couldn't be here, but I didn't see any there. So I'm going to pause and have some tea, and then we'll see if there are any questions that you'd like to see, maybe from either from homework or from the notes from today's review. Because we are looking to have an exam starting on Wednesday. I'm going to have it run through Friday. I'll give you the weekend off, which will be nice. Yay, you don't have to worry about that sort of stuff. So the question from Avery is, can I look at the second example problem from the review from yesterday's lecture notes? And I sure can, absolutely, 100% do that. Let's have a look at that one, because there's some subtleties to that one. That's good that you have questions on it, because that was not necessarily completely simple. So let me pull up that one on my other screen here, I'll just read it out loud so in case folks, but you can go and follow along if you want. It says you put 80 grams of water from the faucet, where the water temperature is 15 degrees Celsius, positive 15 degrees Celsius. And you take that 80 grams, and you put it into the freezer, where the temperature of the freezer is 20 degrees below 0 Celsius, negative 20 Celsius. It's cold. Okay, well below zero. Okay, well below freezing temperature. So it says how much heat must the freezer take out of the water sample to freeze it, and then lower the temperature of the resulting ice cube down to the freezer's temperature, which is negative 20. And it gives you some extra information here just in case. But you could look this up if you're doing it as a homework problem. You could Google it or look it up in the in the table in the book in this chapter, on chapter 10. So it says, note that the heat capacity of water is 1.0 calories per gram degree Celsius. The latent heat of fusion of the ice to water transition is 79.7 calories per gram, and the heat capacity of solid ice, is 0.48 calories per gram degree Celsius. So that is the information that you need to kind of solve this problem. All right. So I'll see sort of what things look at there. And then Abby's got a question too in the work equation. How do you know the value used for cosine? Okay, I'll get to that one right after I get to Avery's question. Thanks, Abby. So you got this mass of water. Let's say you put it in an ice cube tray, so it looks nice, and here it is. Here's this is the water, and it's sitting in an ice cube tray, and the mass of water is 80 grams, and its temperature starting out, it starts out at positive 15 degrees Celsius. Okay, and then the first thing you have to do when you freeze this water, you put it in the freezer, the first thing you have to do is the water needs to cool down from positive 15 degrees Celsius to the freezing point of water, which is 0 degrees Celsius. Okay, so how much heat needs to be taken from the water to do that? And whenever heat is taken out of the system, that you're going to find that Q is a negative number. Okay, so we're going to use this formula for the cooling down or the heating up of substances that's equal to the mass times the specific heat capacity of that particular substance. In this case, that'll be water, times the change in temperature that is experienced in the process of this heat being exchanged. So in this case, what we'll have is we'll have the mass. So there's 80 grams of water that's being cooled down in the freezer. And then there's the specific heat capacity of water. And this is still, the water's still liquid at this point. We're not freezing it. It's not freezing yet. Okay, so I'm cooling down the liquid water, and that's 1 calorie per gram degree Celsius. Gram and degree Celsius are both down in the denominator of that unit. And then we have the temperature change. Now the change in the temperature is the final temperature minus the initial temperature. the temperature that we're cooling it down to here, to get it down to the freezing point where we can freeze it and start to make ice, the final temperature is 0. I mean, that's not the final last temperature it receives, but it's the last temperature that the water is at before it turns into ice. Okay? And when it changes phase from liquid water into solid water, ice, the properties of solid ice are different than the properties of liquid water. And solid ice has a different heat capacity. So I can't say, well, let's take this all the way down from 15 degrees Celsius all the way down to negative 20 degrees Celsius in the freezer, because when it hits 0, it starts to freeze and the properties change. So I can't use the specific heat capacity of liquid water all the way down to the negatives. I have to only use it when it's positive and gets down to 0. So it's the temperature, the final temperature of the liquid water is 0 degrees. And then the starting temperature, so this is final minus initial, is 15 degrees. And these are both degrees Celsius, so that's going to cancel with degrees Celsius there. So when I calculate this, I see that the heat is the heat exchange that happens with the water is 80 times 1 times the quantity 0 minus 15. I put that in parentheses. So I get negative 15 degrees there. And I see that the number I get is negative 1,200. Let's see. Yeah, negative 1,200. And it'll be the grams cancel with the grams here. And the degrees Celsius cancel with the units of the temperature here. And I get just calories. Okay, so that's how much heat is lost. So that's what the negative side heat means here. That I haven't added heat to the ice cube to cool it down. It's not to the ice cube yet. It's still it's still liquid water in the ice cube tray. I've actually pulled heat out. So the heat gets exchanged with the freezer, and the freezer takes heat away from the water, and then it uses the refrigeration process to kind of dump it out into the atmosphere through the heating or the cooling coils. All right, so that's the first stage. That's the stage of cooling down the water to freezing temperature. And then you freeze the water. So then what happens is you've got the freezing stage, and in this you use the latent heat of fusion of ice. Now I'm going to put in an intrinsic minus or an explicit minus sign here. But remember how this works is it's the mass. I'm going to put the formula over here because I started already write the numbers here. All right. So it's the mass times the latent heat of fusion of the water to ice transition. And this is calories per gram of water. So I'll just write what this down is, what this is down right here. So it's minus M times L sub F. It's the mass times the latent heat of fusion that corresponds to the phase transition between going from water to ice or ice to water. Now when I go from water to ice, I've got to take the heat out of the water. When I go from ice to liquid water, I've actually got to add the heat to it. So I'm putting in an explicit minus sign here to indicate that I am freezing the water. I'm taking the water and turning it into ice. And I got to take heat out in that process rather than add it in. If it was an ice cube and I was trying to melt it, I would have to add heat to the water to do it. So I'm just putting in that minus sign here to be consistent with what we had here for the idea that we're cooling this thing and making it, and we're trying to freeze it and then cool it down further. Okay, so let's see what we've got here. We've got, this is 80 grams. It's still 80 grams of liquid water times 79.7. Calories need to be removed per gram, and that's 6,300. So I'm going to put the minus sign from there. 6,376. I think that's what I had. Yep. 6,376 calories need to be removed from the water to turn it into ice. Okay, so that's that. And then now what we've done is, so we've cooled the thing down from 15 to 0. Then we've taken the 0 degree water and frozen it by taking out even more heat. And then finally we're going to cool it down even further, but we're cooling down ice. So that is, we're going to use the same formula, MC times delta T. It's still 80 grams of water. It's just ice now. It's ice water. It's still the same number of protons, neutrons, and electrons. But then I have to multiply times the heat capacity, not of liquid water, but of solid water, of ice, which is not 1.0 calories per gram degree Celsius. It's 0.48 calories per gram degree Celsius. And now the final temperature is going to be negative 20 degrees Celsius. I'll put degrees Celsius this time. And I'm starting, now the water in this part of the process was starting at 0 degrees. It's ice that starts out at 0 degrees Celsius, and I'm cooling it down to negative 20. So this final minus initial, and this gives me a number, which I'll try to put here and not run into my name or my face. Okay, it's 80 times 0.48 times the quantity, negative 20 minus 0. Just being explicit here. And I get negative 768 calories. That's calories there. We'll just say that calories is a tiny little number. But I use 768 calories further. So the total heat that needs to be exchanged, that the freezer, needs to pull out of the water is negative 1200 minus 6376 minus 768. Okay, hopefully that's clear. I'll pause and see if that's clear to folks. Things that I need to, this is calories per gram degree Celsius. I guess I'll put calorie here to make sure that's clear. Was that clear, Avery? Is that all right? Okay. Okay, thanks, Avery. All right, so what I'm going to do now is I'm going to answer Abby's question on, we're going to clear this out, and I'm going to answer Abby's questions. Sorry if I got a little bit of buffering issue here that might be happening. If you experience that, my apologies. We got lots going on in the house here with lots of folks that are streaming or using Zoom and stuff like that at the moment because of we're not the only ones that are doing distance learning at the moment. So sorry about that if you're experiencing that little trouble. But I'm going to answer Abby's question. So in the work equation, how do you know what the value to use for cosine of x or cosine theta, your angle or something like that? So yeah, let's just review what the work formula is. So the work done by any old force, I'll just call it F, would be equal to the magnitude of the force times how far it moves times the cosine of, I like to use theta, but Abby used x, so I'm going to do that. How do you know what the angle x is supposed to be? And great question. So let's look at the situation where you're pushing on a block or something like that. So let's say that you push on a block to the right with a force P. Let's say at the same time there's the normal force that is supporting the object, so I'm going to label that little n. And let's say also there's a frictional force acting on the block, which goes like this. I'm going to use little f to represent that. And let's say that during the process of this pushing, the box shifts its position so that it's further to the right of where it was before. Okay? So in other words, the direction of motion is that way. I'm going to call that for D. So D is to the right. Well, it is the way it is. Okay,